Hello everyone, it's a pleasure for me to present you our works on ellipsoidal set membership state estimation for multi-output system with interval uncertainties. To do this, the outline is the following. I start with an introduction. I will give you some notations and definitions. Then I formulate the problem. After this, I will talk about main results on this paper. I will show you an illustrative example, and I finish by a conclusion and perspective. The state estimation is very important for many control problems, and the difficulty is to estimate the state of the system in the presence of uncertainties in the model. In literature, there are two big classes for the estimation. The stochastic approach, which requires the knowledge of some properties of these uncertainties, as average and covariance. The set membership approaches, which consider that the perturbations and the noise are unknown but bounded. Several sets are used to implement set membership approaches: polytopes, parallelotopes, zonotopes, and ellipsoids. In the case of zonotopes, a lot of methods can be founded: singular value decomposition, the minimization of the volume, the minimization of the segment, and the minimization of the pair radius, which is a trade-off between the accuracy of the minimization of the volume and the reduced complexity of the segments. For the ellipsoids, there is the trace minimization, where the sum of the semi-axis of the ellipsoid is minimized, the determinant minimization, where the volume of the ellipsoid is minimized. In this work, we propose a method based on the radius minimization, which is a good trade-off between the trace minimization and the volume minimization methods. This method will be applied for multi-input, multi-output with interval uncertainties. Let's start with some notations and definitions. An interval AB is given by the inequality x greater than a and less or than equal to b. A unitary interval is an interval -1, 1, denoted by b. A box is a vector which contains intervals as elements. A unitary box is a vector composed by unitary intervals. An interval matrix is a matrix composed by interval elements, and its center and radius are given like this. The set calligraphic Vm denotes the set of the vertices of interval matrix M. An ellipsoid is defined by this set where P is the shape matrix, which is symmetric definite positive, X bar is its center, and draw the radius. When the radius is equal to 1, we can omit it in this notation. It is called the normalized ellipsoid. The following figure represents an ellipsoid which is defined by these parameters. Consider this linear system with x the state of the system, y is the output, and omega is the vector composed by the perturbations and measurement noise which belong to the unitary box. The evolution matrix and observation matrix are interval matrices. Consider also that the pair C delta and A delta is detectable. If we consider the number of uncertainties of A delta is N A delta and C delta is NC delta, then we can write the uncertain parts of A and C as we can see in inequality in equality 3. And we can note N delta and as the sum of NA delta and C delta. If we assume that the initial state belong to the initial ellipsoidal set is 0 and the perturbation and measurement noise belong to this compact set B and X plus and Y, and we assume that the ellipsoid EK contains the state xk, then we want to compute the ellipsoidal set EK plus 1 that guaranteed to contain xk plus 1 at time k plus 1. And the objective is to find the optimal ellipsoidal set that contains the state of the system at each sample time. Let's start with the first result, which is this property 1. Consider a positive definite matrix S, a strictly positive real scalar rho, and nx plus ny positive real scalar 2i. Conditions 4 represent our assumptions with Ti is the matrix of dimension nx plus ny by nx plus ny, having only the element ii equal to 1 and all the other elements equal to 0. Then the following inequality is true, the last one. Here, I will give you the proof of this property. We can easily see that omega k transpose by Ti omega k is less or than equal to 1. From 4b, we can see that rho is strictly positive. Multiplying left and right expressions 4.c by omega k transpose and omega k respectively, and then successively 4.a and 4.c leads to the following scalar formulation: rho minus omega k transpose s omega k is strictly positive with S is definite positive. Using Schur complements leads to the result. Here, the main result of this paper, which answers to our objective. Consider an initial state vector x0 belonging to the ellipsoidal set E0, and assume that at time k, the state belongs to the ellipsoid EK. Given a scalar beta between 0 and 1, if there exists a matrix yk, given a scalar between beta, if there exists a matrix scalar yk such that beta is between 0 and 1, a positive definite matrix S and the positive scalar rho k plus 1 such that the following LMI is vilified for all the vertices of matrices A delta and C delta, then the state of the system at time k plus 1 is guaranteed to belong to the ellipsoid ek plus 1 with the following notations. Yk is equal to p lk. The center of the ellipsoid is given by the equation 7. Here we used calligraphic AK and calligraphic CK to have compact expressions. Let's give you some elements of proof. I will be fast. You can find the total proof in the paper. Denote by ZK the difference between the real state of the system XK and the nominal estimated state, which is the center of the ellipsoidal state estimation set X bar K. Zk plus 1 is given by the equation 8. So we want to prove this implication. If we denote f0 this function and f1 the second equation rho k minus zk transpose p zk. So using S procedure property defined in the paper of Boyd, the condition 9 is satisfied if there exists a positive scalar beta such that f0 minus beta f1 is greater or than equal to 0, which gives the last inequality. Replacing zk plus 1 by its expression on 8 gives this inequality 10. So the expression 10 is verified for all zk if this inequality is verified. and applying Schur complements gives this inequality. After some manipulations, we get the inequality 13, and applying property 1 to the term R by 1 over rho k plus 1 minus beta rho k R transpose, we get the last inequality. And after some manipulations, we get the final result of our theorem. That give you two remarks. For the initialization, given the rate of the estimation convergence beta, the initial center, and the radius of the initial ellipsoid, the matrix P is computed offline in the first step by solving the following LMI. The LMI problem 5 has to be verified in 2 power n delta vertices with n delta is given by this expression. To reduce the number of these vertices to be verified from 2 n delta to 2 power 4 n x, the following optimization problem can be solved. This is obtained by using the scaling technique of theorem 1 of the paper of Alamo. This method is applied for this example of 2 dimensions and 2 outputs. We consider that the infinity norm of omega is less or than equal to 1, and the initial ellipsoid is this one, which is an arbitrary initialization. This method is compared to the offline per-radius zonotopic estimation method. This method uses a constant known observation matrix C, which is chosen as equal to its center. Only the evolution matrix A is uncertain. The proposed online method estimation 5 uses interval matrices for both A delta and C delta. So here we see the bounds of x1 and x2. For the two methods, the state estimation is guaranteed to belong to the estimation set. The proposed method is better in terms of accuracy. Here we see the comparison of the volume of the state estimation sets. As a conclusion, we can say that a new approach for guaranteed ellipsoidal state estimation for multivariable linear discrete time invariant system with interval uncertainties and bounded perturbations and measurement noises has been proposed. This approach is based on online optimization of the radius by solving a linear inequality optimization problem. This method offers an estimation less conservative than the estimation obtained by the per-radius zonotopic estimation, but increase the complexity due to the online computation of the ellipsoidal radius. As perspective, we can apply the proposed method to fault detection and fault-tolerant control purposes. Thank you for your attention.